One of the most interesting curves to investigate is the addition of a strong base to a weak acid. In this graph, we can see a sharp increase in the pH initially, and then the pH change is very gradual, before bang, it suddenly changes again. This region of minimal change in pH is referred to as the buffer zone. In the weak acid solution at the start, a small percentage of weak acid molecules, HA, are dissociated, and this means there are also H+ ions and conjugate base ions, A-, present. An equilibrium forms between the three. As the concentration of H+ and A- ions are the same and very low, the position of equilibrium is based on both the A- and H+ concentration. However, if a strong base, sodium hydroxide for example, gets added, hydroxide ions will react with the molecules of the weak acid, forming water and conjugate base ions, quickly increasing the concentration of A- ions in the solution. This means the concentrations of HA molecules and A- conjugate base ions soon become much larger than H+ ion concentration in the solution, and this enables it to start acting as a buffer system. As more OH- ions get added, they continue to react with H+ ions in the solution to form water, and this would cause the H+ ion concentration to decrease. However, the position of equilibrium between HA, H+, and A- will shift to try and counter this change by more HA molecules dissociating. This tops back up the H+ ion concentration in the solution. As a result, the H+ ion concentration stays roughly the same and the pH changes only a little bit each time more base gets added. pH change is minimized by the buffer system, just like for a normal buffer solution. Eventually, the concentration of HA starts to fall too low for the equilibrium system to cope, and bang, this is when the pH starts to increase rapidly again. If you're at all unsure about how the buffer is working here, please check the video on buffers. The link is in the description below.